much as an introduction. Good afternoon, everyone. In this talk, I will try to summarize our recent work on the role of cathodic current in plasma-electrolytic oxidation process. After a brief introduction, I'll go through details of breakdown of anodic films, the role of the cathodic current in PEO, and the main research part of this work. So what is plasma-electrolytic oxidation? It's generally the oxidation of metals, followed by its breakdown under the high voltage polarization, which results in unique morphology, composition, and good adhesion to the substrate. Up to now, we know a lot of examples about the plausible applications of PEO coatings. However, examples of real practical industrial implementations are limited by several niches. This happens because we don't know how the process really works, and trial and error approach here is not really productive because of large number of variable parameters. And as a result, we must dig deeper in order to provide better commercialization of this technology. Contrary to popular belief that we will never truly understand this process, I disagree with this, and the process is understandable, but we should not oversimplify it. Here you can see the pyramid of the elementary sub-processes and phenomena in the plasma-electrolytic as a technology. It starts at the bottom from basic passivation, goes up to microstructure and some application-related elements. And what we have when we apply trial and error approach, we start from the bottom, and then we will try to figure out how we can apply this coating. However, real engineering approach requires an opposite direction. So we should start from application and then go down, arranging process in a certain way in order to get required properties and performance. So what is the working electrode in plasma-electrolytic oxidation? It's a metal covered with oxide and immersed in suitable electrolyte. As a result, we have two conductors, like electronic conductor and ionic conductor, separated by a layer of oxide. For valve metals, the term introduced by Günther Schulze in the 1920s, there is a characteristic combination of properties for such type of metal oxide electrolyte systems. So the anodic current happens via ionic migration through the field, which provides the growth of the field. However, cathodic current happens via electron injection from the metal to oxide and corresponding cathodic reaction. So as a result, we have usually much larger negative current rather than positive one. And if we apply alternating current to such sort of system, we will have a rectification. A few words about ionic current, as it is the main component or is the main process of the coating growth. It's generally accepted that it can be described by a local high-field Hoping mechanism, and as a result, we have a very good correlation between voltage and thickness of this anodic shell. It's also accompanied by energy dissipation, majorly by the Joule heating of the ionic current of ionic transport, as well as by heat dissipation of the oxide formation. However, it's significantly less. So why can't we have an electronic current in anodic direction? The problem is that electrons, both in oxides and in electrolytes, are associated, they are not free, they are associated with molecules of solvent or with anions in oxide. So if we consider like the Venn diagram of this triple junction, we will see that Fermi level of the electrolyte species and the bottom of the contaction band are separated by a significant potential barrier. However, we know that energy of the electrons is directly connected with the potential of the electrode. So what if we apply a higher potential? In this case, we will see that if we apply enough high potential that the electrolyte species reach the bottom of the contaction band, the total potential drop will include two components. One is the drop within the the oxide electrolyte interface, and another is the drop within the oxide. In such a situation, the electrons appeared at this interface will be accelerated within this electric field, and it may result in the multiplication of the primary electron of the anodic reaction, causing avalanche multiplication and breakdown. And this is a typical characteristic for valve metals, that when those species reach the bottom level, the field already high enough to generate the avalanche breakdown. And as a result, we have two parallel processes. Both requires high field conditions. First is the anodic current or ionic current, and the second one is the electronic current by means of breakdown. And the art of PEO is to find the proper balance between those two components, because one is responsible for coating growth and another is for the creation of specific morphology. We know that bipolar PEO process has significant benefits such as better process control, higher energy efficiency, better coating uniformity, and some drawbacks like more expensive equipment, complex design, and difficulties with optimization. However, there are some particular experimental features of this electrical mode. For example, if we apply just only positive pulses, when the voltage reaches the breakdown level, current sharply increase, and we have localized breakdowns on the surface of the sample. However, if we apply a negative pulse, the following positive pulse experience a characteristic hysteresis. So the current of much lower voltage and discharge chain appearance into a much smaller pattern of much smaller discharge, or uniform glow, or even complete extinguishing of the light emission. What's important here is, first, is that the characteristic parameter of such a regime is the ratio between negative and positive currents, average values, and that such sort of electrochemical response can be detected in situ in experiment. Since the invention of the bipolar electrical regimes, IC regimes, a few hypotheses were suggested to explain some features of such processes, and as we can see, some of them are internally contradictory, and even altogether, they are not able to explain the full list of the most typical features of such processes. So we need something else. This set of hypotheses is not really working. So what may happen under the cathodic polarization in our system? First, it may be an absorption of cations. Second, it may be evolution of hydrogen if oxide is in the conductive state, or there may be even an insertion of cations followed by the neutralization inside of the oxide. This is a relatively busy slide, and the main idea here is that the reactant in the cathodic reaction is the water. However, the cationic composition of the electrolyte is important to create a specific structure of the electric double layer, which affects the interaction between oxide and water. So the only possible reaction which may be responsible for the cathodically induced effects is the insertion of hydrogen into the film. If we have a look to a typical bipolar waveform, which is a very good example because it has very well distinguishable steps, we can see that step A may be associated with anodic oxidation and micro-discharge. Step B is just relaxation of residual charge. Step C is a negative pulse, it's recharging of the surface and change the local pH. And then we have step D, where no current and no voltage are different from zero. So what is going on here? From practice, we know that duty cycle, even for negative pulse, is also affecting the resulting coating. So in order to identify what is really going on there, we designed a complex electrical mode which composed of the working pulse strand or the coating deposition, which was interrupted by an introduction of the diagnostic pulse train, the core of which is the voltammetry triangular pulse, preceded by some positive or negative pulses. And variable here was the duration between like a positive and negative pulse and that voltammetry response. And those interruptions happened in a sequential manner. The response here was the hysteresis of the diagnostic pulse. And what we have found is that after a negative pulse, after a sharp increase of the hysteresis current, it exponentially decreased. But after the positive pulse, starting with some minimum value, the hysteresis exponentially increased. And it looks like we have some sort of reversible process. So negative pulse, like charging something, positive pulse, like discharging something. What can it be? So we assume that it might be a hydration and plays an important role here. It's also interesting that this microstructure of the barrier layer in soft sparking mode represented by much denser and less porous material, whereas in microarcing coating, we can see many small pores and presence of some crystalline phases. It's also interesting that EDS analysis of the barrier layer revealed that in soft sparking conditions, we have a depletion of aluminium species, which may be also an indirect evidence of the presence of hydrogen in various forms, which cannot be detected by EDS. And summarizing above findings, we proposed following hypothesis. It is based on following fact that original non-uniform current density distribution, which may be a result of porosity, cracks, or anything else, result in the anodic process into a localized breakdown of the barrier layer. Whereas when we apply alternating current, cathodic pulses introduce some changes in the barrier layer, which introduce higher electric conductivity, and this sublayer works as a current redistributor. So in this case, we have a planar type of energy dissipation here versus vertical columnar type of the energy dissipation. And this can be also evident from the comparison of micro-discharge appearance, and the most important, from the shape of the interface to the metal and oxide interface. So here is wavy, and here is almost flat, or quite flat. So what is really happening within the oxide? Could it be a hydration? Could it be intercalation? The hydration is just chemical process, but it's unclear how it can be associated with cathodic current. Intercalation is purely electrochemical process, and it's unclear how it can provide a self-injection after the positive pulses. So trying to couple those two mechanisms, we created a relatively complex cycle, which, however, we will have to reject further. A few words about memristor, or memory resistor. This is so-called missing element. The physics of memristor is still debatable, but what's important for us that there are some sort of memoristic-like devices. The main idea of memristor is that they store the information about the past charge. And some devices built, for example, by Strukov from titanium dioxide sandwich between two platinum electrodes, and he considered this system a following way. When titanium changed its oxidation state because of past charge through the system, the overall titanium dioxide is split to two components of like doped and undoped, and the risk of undoped is the function of quasar charge, and as a result, overall electrical response of such sandwich experience a characteristic hysteresis. If we had a closer look to our proposed active zone concept, we have modified layer within the barrier layer, which can be exactly considered as doped and undoped oxide. So the equivalent circuit proposed by Strukov can be applied here as well, and we can do some calculations. However, apart from the interfacial model suggested by Strukov, we also have to consider an alternative way, where depletion or intercalation happens by means of change in concentration rather than the interfacial drift. And here you can see two different equivalent circuits corresponding to those mechanisms. Previously, we suggested that deintercalation and intercalation are reversible processes. One is just cathodic and another anodic, so both electrochemical. But this assumption contradicts with experimental observations when sub-sparking results in even higher efficiency of the process. However, in this case, it would consume part of the anodic current, and this would not be the case. As a result, we have to reject this as a main component and suggest another thermal-induced mechanism, which positive features are that it's capable both with atomic hydrogen atoms intercalation and with hydration mechanism together. Here you can see some results of the modeling for those corresponding equivalent circuits, and we can see that for concentrational model, the voltage range is kept almost constant, but the magnitude of the hysteresis current stepwisely changed with degree of intercalation. However, for interfacial model, we see that increase in intercalation degree and shift of this interface deeper into the barrier layer should result in the decrease of the threshold voltage between off and on state of the hysteresis current. And those behaviors are very different, so we should be able to observe this difference in experiment. The experimental design is similar to what we had previously, but slightly changed. So we again have working pulse strain interrupted by a diagnostic procedure with potential dynamic triangular pulse, which here is preceded by either negative or positive pulse with variable magnitudes. And the hysteresis current and hysteresis charge is the integral current are the main responses here. And what shows the experiment? If we apply only negative pulse, following triangular pulse shows characteristic response. So the higher negative pulse, the higher the hysteresis current within the same voltage range. However, if we apply additional positive pulse between negative and diagnostic pulse, what we will see in the diagnostic pulse analysis is that increase in positive pulse reduces the hysteresis current, indeed, or hysteresis charge, but it happens in absolutely different manner by means of change in the threshold voltage. And if we compare this with what we had got from the modeling, we will see that there is a very similar situation for concentrational model, which is probably responsible for negative pulse, and the interfacial model, which is probably responsible for the positive pulses. So and those facts are indirect evidence of the fact that our hypothesis of the active zone narrowing is relevant. Yeah? And this conception of the narrowing at the active zone is also fruitful for the control to control the balance between coating growth and avalanche breakdown of the film, because we very well know that the thicker the film, the lower the critical breakdown field within the film. It means that thick film will break down at much higher or much lower, electric field, whereas thin film withstand a much higher electric field without a breakdown. However, the ionic current, which is independent almost on thickness, doesn't depend on the thickness of the field. It's just a proportion to the local electric field within the field. And we have two different situations. First, for thin films, we have ionic current much higher than electronic current. And this situation is typical for anodization or early stage of the plasma-electrolytic oxidation. And the second situation for thick films, where electronic current is significantly higher than ionic one. And this happens for thick coatings by means of regular microarc generation, breakdowns, and so on. And what is the role of narrowing here is that by application on negative poles and shrinking this dielectric part, we locally bring the thick coating into a state when it behaves as a thin one, and therefore we may suppress discharging completely in some circumstances. Another interesting feature of bipolar electrical regimes in here that it promotes generation of high temperature phase. On aluminium it's alpha phase, and it's also interesting that it's generated in the middle of the coating. It's not on the metal oxide interface, it's not on at oxide electrolyte interface, is just somewhere in between. In order to explain this, we have to assume two opposite trends. One is the temperature and another is the grain size, and as a result we had a relatively narrow area where both factors match the conditions for gamma to alpha transformation, and we call this narrow region as a reactor. And this can be considered as a well-known concept from the chemical engineering as a plug flow reactor, which takes gamma phase at the input, and the temperature profile is defined by the structure of the active zone or barrier layer. And if we have a look to the simplified equivalent circuit of the PEO coating, we will see that one resistor which is responsible for anodic reaction, which generates gamma phase at the input of this reactor, is shunted with a capacitor, and in series it's connected with the resistance of loss of ionic current, which create the temperature profile within this reactor. And as this circuit includes a reactive element, a capacitor of AA, the frequency response of this system should be quite specific. And the idea is that we should have a maximum at certain frequency which provides the maximum conversion of the gamma phase into alpha. Okay. As a result, we have two fundamental parameters here: the R factor or current ratio, which is responsible for the geometry of this reactor, and the frequency, which is responsible for the energy dissipation within this reactor. So if we again compare the suggested active zone narrowing approach with previously suggested, we will see that it's capable with explanation of the most characteristic feature of bipolar PEO process. However, we still have a question about what is really happening there. Is it a hydration, or it's some intercalation, or maybe something else? The question is still open, but it's still fruitful model because it helps us to predict the behavior of the system. And now we are getting to the main part of this talk, is the research part on cooperative effect between the current ratio and frequency. Here we use the bipolar electrical mode at constant positive poles and variable negative poles. The current ratio was in the range between 0 and 1.6, and frequencies were changed between 50 Hz and 5 kHz. We use pure aluminium as a model system and simple diamond silicate electrolyte. The system was characterized by means of different characteristics. I will speak about them later. So first of all, we can consider how the micro-discharge pattern depends on the frequency and current ratio. Here you can see the final step of the process before its termination. The overall duration of all processes was set to 30 minutes. So you can see like final seconds of the process displayed here. And what's interesting is that we have three characteristic regions. First, the largest one is in this region, the most of this map, and it looks like arcing or very aggressive localized discharges. The second one is a soft sparking region in the green frame, and as well we can also see some mixed type of behavior where soft sparking at the background is overlapped with some localized orange breakdowns, similar to what we had in Microarc region. It's also informative that similar trend we can observe in microstructure of this coating. So here you can see a cross-section of micrographs. But what's interesting here in regards of that microarcing region, that it demonstrates two types of the morphology. Say high frequency corner or region shows columnar type of the porosity, I would say. However, low R factor, low orientation region shows like a laminar, almost completely detached coatings in this in this region. In regards of the soft sparking, we can see a very dense, flat coatings here, which oxide metal interface is almost flat here, in contrast to other regions. We'll have some intermediate feature here. However, the most interesting things are associated with the phase distribution. So here you can see relative proportions of alpha, gamma, and light peaks in XRD pattern as a function of two parameters, frequency and R factor. And we can see that we have three well-distinguishable regions where each phase dominates. What's interesting here, I'll focus your attention to the alpha phase here, that if we plot the proportion of alpha phase at 3 certain current ratio as a function of the frequency, we will see a following type of graph. What's interesting here, that they start with certain level at low frequency, then experience some maximum at middle frequency range between 500 and 1000, and then they quickly drop down at higher frequency. And if we compare this with what we predicted from the plug flow reactor model, that there should be a certain frequency at which the conversion to the alpha phase reaches its maximum, this graph is exactly what we have predicted. So this model is quite fruitful for prediction of the coating properties. A few words about the phase formation features. So the primary reaction, we have two primary reactions here, is the oxidation of aluminium, say, into gamma phase, and the acquisition of silicate as amorphous silica, which may be converted into different phases depending on particular conditions. For example, the gamma phase may be converted by heating into alpha phase, or if they are mixed together, then waves will combine. As it was shown above, we have three characteristic regions within the current ration frequency map. The region enriched with light shows that cross-section of the coating, the enriched of the part of the coating enriched with silicon is at the outer part of the coating. So we can assume that we have here some sort of shallow heating. So reaction, the fusion of this mixture happens within the outer part of the coating. In the second region, enriched by alpha phase, the reaction happens inside the coating, deep inside the coating, and this reaction is conversion of gamma to alpha phase, whereas outer part is not really affected. And the third region, enriched with gamma phase, shows that there is no certain regions with predominant certain elements. So it's just a fine mixture of different components of amorphous silica and gamma, crystalline gamma phase, which didn't undergo a reaction. And the difference probably is because we had much longer pulse in this case and much shorter pulse in this case. So this tells us how we can select a proper electrical regimes in order to introduce solid particles, nanocontainers, nanomaterials into the coating, either reactively if we need it, or non-reactively if we want to preserve these containers from destruction. Now we know almost everything about this bipolar waveform. and we can deconvolute it into individual components. For example, positive poles can be represented as a sum of three components: as a capacitive current, which is responsible for this peak; as a hysteresis current, which is connected to previous negative poles; and the Faraday current, which is responsible for particular anodic oxidation and micro-discharge generation. The step B is discharging and relaxation, which we also know the formula, how to calculate this shape. The negative pulse is a sum of characteristic inductive response and recharging. When we switch from positive to negative, we need some recharging, and this current peak associated with these processes. And step D, which we revealed recently, is the chemical relaxation, which can be also evaluated according to this formula. So we need some sort of calibration of this model, because we have a lot of numerical parameters like resistance, characteristic capacitance, so we unable to derive them directly from the experiment. But what we can do is just to find proper values in order to match experimental point with calculated waveform, and here it was done. Assuming that model parameters are not dependent on the frequency, which is not completely true, we can consider how those three components of the positive pulse redistribute each other within the current ratio and frequency matrix. What we can see is that we again see three characteristic ratios: the hysteresis current at the higher current ratios, the capacitive current at higher frequency, and Faraday current at low frequency and low current ratios. And if we compare with this with the phase composition shown above, we will see that hysteresis current correlates with the presence of alpha phase. Yeah, it's not exactly the same shape, of course, but the trend is very clear. The capacitive current correlates with presence of gamma phase, and the Faraday current correlates with the presence of light. So, summarizing this, we have a very powerful powerful model with a high power of predictability, and this may be really important for understanding of the phase distribution in fields on the cortex-shaped parts. So now we are getting back to original pyramid. So what we have done within this talk, we get through first 6 steps under quasi one-dimensional approach, because we didn't consider any spatial related features. And the next step is a microstructure, which requires solving the problem in 2D or even 3D formulation. However, this is a different story. So thank you for your attention.